So today we're going to be looking at some derivatives of exponential and logarithmic functions. So before we do that, I think it's important maybe to review just a little bit about exponents and logarithms. So we're going to look together at this warm-up that I would give my face-to-face classes, but I think it'll be helpful here too. So the first thing is, what is e? E is not a variable like most letters are. E is the exponential constant. And it stands for the decimal 2.718281828. And then I'm going to put a ... there, implying that the 1828 will actually repeat over and over. So we'll put a bar above that. Okay. So when you're being asked to find ln of x, or natural log as you would say it, okay, this is the natural log function. Okay, so what it's asking when you're asked to find the natural log of x is you're being asked to find what power of e do I need to raise, what do I need to raise e to give me x as an answer. Okay. So when you're being asked to solve this, for instance, so this is the question that's being asked. What do I need to raise e to give me e to the x? Okay, so that means that the natural log of e to the x is actually just x. Okay, think of natural log and e as inverse operations. They undo each other. So if you know that, again, these are all from Business Math 1. That's why this is part of the warm-up. So when you're being asked to solve this, this is what this is asking. What do I need to raise e to give me 1? And notice anything at all to the 0 power is 1, right? So the natural log of 1 is just 0, because that's the exponent required to raise e to so that you get an answer of 1. And so I like to tell my students, you know, e is not a number that some mathematician came up with to make you miserable. It is always associated with exponential growth. So it's a value that is naturally occurring, kind of like pi is naturally occurring when we're discussing measurements of circles. E is naturally occurring when we're discussing exponential growth. So if you're a little shaky on logarithms from the class before this one, you might want to pause the video and maybe go look some of this stuff up. You really need to know e to powers, and you need to know how to deal with ln of x, and also just regular old logarithms. Okay, so let's get to the actual lesson. So we are skipping around a bit, but we're going to look at, just like I mentioned at the beginning of the warm-up, we're going to look at the derivatives of exponential and logarithmic functions. I kind of consider these to be sort of special cases. So how do we find the derivatives of these maybe more unusual functions? Okay, so I know we just did it in the warm-up, but I want to make sure that it's in your notes too. So if we review as we go, e is the exponential constant. It is the number 2.718281828, and then that repeats. You usually see it with like an italics N or L, I mean, that's why I kind of show it like that. So this means natural log that should be a U there, or it's the log with a base of e, and you literally can say it as natural log or as log base e. So I always take class time to kind of show this, but I want to look at the graphs of e to the x and ln. I don't want to spend a ton of time on this, but I do want you to kind of know what I mean when I say that e and ln are inverses. So if we can just sketch a graph where we go out maybe 8 in every direction. And so back when you were learning how to graph things, we're going to graph e to the x, okay, and then we're going to also graph its inverse, but for now let's just do e to the x. So when you don't know what a graph looks like, you can do an xy chart, okay, and you can just say, hey, I'm going to pick some x's, and then I'm going to plug them into the equation to find out what the y's are. Okay, so literally you could use your calculator for this. Okay, so you would plug this into your calculator, and if you do, you're going to get you're going to get a bunch of decimals. So we're just going to round them. So 0.14, 0.37, 1, 2.72, and 7.39. Okay, just real quickly, literally all I'm doing is plugging them into the calculator portion and saying e raised to the -2 power. Okay, notice that gives me 0.135, which I rounded up to 0.14, and then I'm changing the exponent as I go. So notice some of these points aren't very pleasant to graph. So I've got the point 0.1, and then I've got the point 1, almost 3, correct? And then I've got the point 2, and then a little bit past 7. But then on the negative side, I have -1 and 0.37, so in other words, the graph kind of has two pieces, one piece that goes up sharply, and then one piece that just keeps getting smaller and smaller, okay? We've talked about this already this semester. It technically has a horizontal asymptote at 0. Okay, so that would be the graph of e to the x. So let's contrast that with the natural log of x. Now, inverse operations are operations where we have flipped x and y. Okay, so all that means is, notice all the x's are going to move over to the y column, and vice versa. Okay, that's the definition of inverse. So if you use your calculator and you find the natural log of 0.14, you will get about -2. About, because this is a rounded version. So if we graph these guys, so now we have the 0.10. Notice I'm doing that in a different color. You have 2.721. So maybe about right here. 1, 2, 3, 4, 5, 6, 7, right? 7, 2. And then graph these points as well, the best you can anyway. So notice the structure of this graph is similar, but rather than having a horizontal asymptote, it actually has a vertical asymptote. Okay, so this is the graph of g of x. And in fact, in algebra, we learn that inverses have graphs that are reflected over the line y equals x. So if you picture the line that I drew in black here, y equals x, notice these are flipped versions of each other. So whereas this one has the red graph, the e to the x graph, has a horizontal asymptote at 0, notice the green graph has a vertical asymptote at 0. Okay, but these are inverses of each other. Okay, so e to the x and ln of x are inverses. So hopefully that'll kind of help you as we talk about the derivatives later on. Remember, derivative is still the slope of the tangent line. And the derivatives of exponential functions and logarithmic functions I really just consider to be special cases. Alright, so if you want the derivative of the exponential function, so remember this d dx notation just means, hey, find the derivative of e to the x. Okay. Interestingly enough, the derivative of e to the x is always itself. Okay, so the derivative of e to the x is itself. Again, it's a special case. So let's do a couple of these, and then we're going to come back to this in the next couple weeks when it gets a little more complicated, but for now we're going to stay pretty general with this. So let's say that I told you to find the derivative, and notice that's what this means, right? Find the derivative if f of x is equal to 5x. Okay, so the derivative is anytime you have a constant being multiplied, remember you just bring that down. And then, interestingly enough, the derivative of e is just itself. So I end up getting something that looks like what I started with, right? But remember, this is the equation for the slope of the tangent line. Okay, so notice this is different than doing x to a power. This is e to a power. Okay. All right, so let's do one that might draw in something we did last week and kind of combine it with what we're doing this week. So d dx, remember, means derivative. So find the derivative of 3x squared plus 2x plus x over 3 plus 4 over x plus 5 plus e to the x. Okay, so remember, this means derivative, right? So the first thing that I would do if I were you is I would rewrite these two guys. You need everything to be in exponential form if you can. Okay, so just so you know, this is 1/3 x. That's how you would rewrite that. Okay, notice the x stays on top. Okay, so it's just 1/3 x. This, however, would be 4 and then x to the negative 1 power. Okay, notice I'm not finding the derivative right now. I'm just telling you what these are in exponential form. So now let's find the derivative. Remember, the derivative involves, I'm just going to do this for 1, moving the power around to the front and then reducing the power by 1 for the power rule. Okay, so the power rule is going to apply to all of these guys except maybe this one and this one. Okay, so if you move the power around to the front here, you get 6x to the first. If you move the power around to the front here, you'll get 2 and then no more x's, right? So if you think of this as an understood first power and you move the power to the front, then you'll just get a 2. Same thing here, right? If you move this power around to the front, you just get 1/3. So again, if you think of this as a 1 and you move it to the front, 1 times 1/3 is just 1/3, and then you would have x to the 0 power, which is just 1. But here you need to be careful. If you move the power to the front, you're going to get -4, right? And then you're going to take away 1 from the power, so that's going to be x to the negative 2. And then the derivative of a constant last week, remember, was always 0. And then here's my new thing. The derivative of e is itself. So if I clean up things and I combine like terms, notice these two guys are like terms, so you could use your calculator if you wish. But this is 6/3 plus 7/3 is what you get when you combine those. And then remember, I don't want to see negative exponents, so I'm going to rewrite that as -4 divided by x squared. Okay, it's x squared on the bottom because this is a negative exponent. And then just plus e to the x. So even this complicated thing is just the equation for the slope of the tangent line. Okay. So let's look at one more. Honestly, I'm really not going over the new rule as much as I am just kind of reviewing some of the rules from last week. So what if g of x equals 3 square root of x plus 1 over x squared plus 2 e to the x, and I told you to find g prime of x, which means go find the derivative. So the first thing is you need to go term by term and make sure it's written in the proper form. Is it written in the form that we can actually take the derivative? Okay, so in other words, we want to rewrite this guy and probably this guy. Okay, so how could I rewrite 3 square root of x? Well, it's the same as 3x to the 1/2, right? Because roots are fractional exponents. What about this one? This would be x to the negative 2 power. So if I want to do the derivative, notice I always say, hey, I'm doing the derivative now by using the notation. I need to do the power rule, right? So if you bring the power around to the front, 1/2 times 3 is 3 over 2. Okay, but then it's going to be x to the what power? So think to yourself, what happens when I subtract 1 from 1/2? I get negative 1/2. You can use a calculator if you must. Okay, what about for this guy? Notice we're going to bring the power around to the front and reduce the power by 1. So it's going to be minus 2x to the negative third. And then last but not least, our new rule, which is the derivative of e is just itself, as long as it's just e to the x. So in the end, make sure you write everything in the form that I've requested. So it would be 3 over 2 x to the 1/2, right? Because that moved to the bottom because of the negative exponent. Then it'd be minus 2 over x cubed, and then plus 2 e to the x. Okay. If you wish, you can write this x to the 1/2 as the square root of x. So if you wanted to write this first term as 3 over 2 and then a square root of x, you can do that as well, as long as you keep it on the bottom. Okay, so that's the rule for e. The derivative of e to the x is always just itself, e to the x. Okay. By the way, I'm not going to write this for this one, but this is also the equation for the slope of the tangent line. That's always what the derivative is. So on the first class day, or your first video lecture, I should say, I reviewed with you the 3 logarithm rules. So I'm going to review them again here, but briefly, because you can go back and watch that first video, but we're about to use these. Remember, these were called the product rule, the quotient rule, and the power rule. Okay, I'm going to put a star by the power rule. That's probably the rule we're going to use more often than the other one. So just briefly, the product rule says that if you take the log of x times y, it would be the same as if you did the log of x plus the log of y. The quotient rule just says that if you have the log of x divided by y, it is the same as doing the log of x minus the log of y. And then last but not least, the power rule is for when you're doing the log of maybe x raised to a power p. And when you do that, the p moves around to the front. So you're allowed to change this into p times the log of x. Okay, just also remember that these rules work for any base at all. So they also work for ln. So remember, ln is base e. So these rules work for log, base, whatever, but including the special case ln or natural log. Alright, so the next rule that we're going to discuss is, or the next special case is, how do you do the derivative of the logarithmic function ln of x? In other words, how do you find the slope of the tangent line if your function involves natural log of x? So for now, just think of this like a special case, and we're going to keep this pretty simple. But the derivative of ln of x, okay, the derivative of ln of x is always just 1 over the inside function, which is x in this case. Alright, so let's maybe do a few examples here. Again, kind of like before, I'm really just reviewing you on a lot of older stuff too. So if I give you that f is 10 over x minus 3x squared plus 3 ln of x. So I just want you to get in the habit of rewriting things when they're not in the proper form. Okay, so I would want you to rewrite this guy as 10x to the negative 1 before you ever start with derivative, because we want to be able to use our formula. So the derivative is, move this power to the front, right? So negative 10 and reduce the power by 1. Move this power to the front, right? So we're going to get minus 6x to the first. And then lastly, here's our new rule, right? So what happens with a constant? It gets pulled down. But then the derivative of the function ln of x is always 1 over x. So simplified up, we get negative 10 over x squared minus 6x plus 3 over x. If you wanted to change the order that you listed these in, that would be okay, but it's not necessary really. Okay, so the derivative of ln of x is always just 1 over x. So what about, though, if you're given something where you're asked to find the derivative of something that's not plain old ln of x? Okay, we only have a rule if it's plain old ln of x. Okay, so what we're going to do is we're going to see, do we have a rule listed above that we could use to rewrite this? Okay, notice we have the natural log of something raised to a power. Okay, so I'm going to continue this ddx notation because I'm not doing the derivative right now. I'm using algebra to write this in a different way using the power rule. So remember what the power rule says. It says we're allowed to move the power around to the front of a logarithm term. So now we're really just being asked to find the derivative of 4 times the natural log of x. And now we've already done one like this, right? The 4 is a constant, so it moves over. And then the derivative of ln of x is just 1 over x. So in the end, the answer is just 4 over x. All right, so one more. And then we're going to expand to maybe a different type of special case. So if g of x equals 2 plus 3 ln of 1 over x, then I want you to find the derivative. Okay, so again, this doesn't look right, correct? We need to rewrite this. So we're going to do a couple of steps here. So notice I'm not saying the derivative because I'm actually not doing the derivative right now. I'm just trying to rewrite this in a form that I'm more comfortable with. I need to have ln of x when I'm done, not ln of something else. So I'm going to rewrite this as 2 plus 3 ln of x to the negative 1. Okay, so all I did was change 1 over x to x to the negative 1. But now notice, using my rule of logarithms, I can move that around to the front. So I'm still not finding the derivative. I'm still dealing with the original function. I'm just rewriting it differently. And we should change that to a negative. Sorry about that. So we can say plus a negative 3 or minus 3, however you want to say that. Notice now we can find the derivative, right? So the derivative of a constant is 0, constant by itself. The derivative of this, we're going to bring the constant down, and the derivative of ln of x is our special case. So in the end, it's just negative 3 over x. Okay, so the derivative of e to the x is itself, e to the x. The derivative of ln of x is 1 over x. Okay, so that's why I consider those to be special cases. They really just deal with, one particular type of problem. So now that we know kind of the special cases, we can expand this out into really any logarithm we want. So now we're going to find the derivative of any kind of logarithm, whereas before I just told you how to find just the special case ln of x, or natural log. And hopefully you're going to see that it looks similar to the one that we just did. So if you want to find the derivative of any log with any base of x, it is going to be 1 over the natural log of b, and then times 1 over x. Okay, so notice the only part new here is this right here. Okay, by the way, this is a constant because b is going to be a number, like maybe it'll be base 4, or maybe it'll be base 10 or something like that. So it would be 1 over the log of whatever the base number happens to be, and then times 1 over x. So it's just going to take some practice for you to get this new kind of special cases down a little bit. So what if I told you to find this derivative? So hopefully you notice that, hey, I'm not going to be able to leave this in this form. I only know how to do things where it's log of x. Okay, so I'm going to need to use the power rule, right? So I'm going to rewrite this guy as 5 and then log base 4 of x. Okay, notice all I'm doing is rewriting the original, not doing the derivative yet. But now I can do the derivative using my rules. So the constant 5 moves down. And now I need to figure out what's the log base 4 of x when I do its derivative. And the formula is it's 1 over natural log of the number of the base times 1 over x. Okay, so to kind of clean that up a little bit, basically it's like 5 over the natural log of 4 and then times 1 over x. Okay, so all I did was literally combine the 5 times the 1 over natural log of 4. All right, let's do one more and then we're going to look at different types of exponential functions and how we can take those derivatives. So find the derivative of 3x cubed plus log base 5 of x to the 10th. You may or may not see the parentheses here around the x to the 10th. Sometimes it'll have it, sometimes it won't. So before I begin, I'm going to rewrite this guy. Remember, the rules of logarithms say I'm allowed to move this power around to the front. So when I go to find the derivative, let's keep that in mind, right? So this would be the same as finding the derivative of 3x cubed plus 10 and then log base 5 of x. So notice I continued this notation because I haven't actually found the derivative yet. But now let's go ahead and do it. So if I bring the power around to the front, 3 times 3 is 9. Reduce the power by 1, you get x squared. But then here's a special case, right? So the 10 is a constant, it pulls down. And then the derivative formula is 1 over the natural log of the number base, and then times 1 over x. So in the end, we would probably rewrite this as 9 squared plus 10 over the natural log of 5, and then times 1 over x. Okay. And again, not to beat a dead horse, but remember, this is the equation for the slope of the tangent line. No matter how ugly the derivative is when you get it, that is always what it represents. So once you get the hang of these, you'll find they're not as ugly as they might appear. You don't really even have to have a super strong understanding of logarithms as long as you just remember how to find their derivatives. So the last special case, and then we're going to look at maybe some application problems after we do a couple of these, is the derivative of the general exponential function. In other words, what if it's not e to the x? What if it's something else to the x? So So how do I find the derivative of y equals b to the x? Where b can be anything, so maybe 2 to the x, or maybe 5 to the x, or something like that. So let's do 5 to the x. If f of x is equal to 5 to the x, oh, I guess I need to give you the rule first. Just kidding. So ignore that for a minute. We'll do that in just a minute. The derivative of b to the x will always be itself times the natural log of b. Notice that looks similar to what we did for the e to the x, although we have an extra little constant being multiplied here. So sorry about that. Sorry for skipping that. So now let's do example 9. So if f of x is 5 to the x, let's find its derivative. Notice this is not e to the x, right? It's some other base to the x. So we're going to use this new rule. So the derivative will literally be itself, but then times the natural log of 5. Okay, like whatever the base is, you're going to times it by the natural log of that. And that's it. There's not really a whole lot to this rule. I think the ln and the log ones are a little more challenging. Okay, so let's do one more. So, I don't know why I wrote that so big, but 5 over x cubed, and then plus 3 times 4 to the x. Okay, so notice this notation means, hey, find the derivative. So maybe before we start though, let's maybe write down what this is. This is 5x to the negative third. So if we do the derivative, it's going to be move that power to the front and multiply, and then reduce the power by 1. So this is just power rule from last week. But here's where we have something new, right? So the constant's going to pull down. And then we're going to follow our formula, right? So the derivative of 4 raised to a power is itself times the natural log of that number. So maybe a little tricky, we would write that in that way, right? By the way, do not multiply the 3 times the 4 because 4 to the x is together. So remember your order of operations, exponents comes before multiplication. So this would just be, I'm gonna write it like this so that we're not tempted to do that. I'm gonna move the ln of 4 and kind of squeeze it in between them. But this is as far as we can go with this. Now, how you wrote these order-wise, it wouldn't matter. I just like to write it like this so I'm not tempted to try to do the 3 times 4, which I can't do anyway. Think of this like the 4 and the x are like a pair. We can't separate them. So we definitely don't do 3 times 4 to get 12 there. So make sure you know the difference between these two types of functions. So make sure you know that when we find the derivative of something like x squared, okay, notice the x is the base, right? And we have a number exponent. When you have a number exponent, you're going to use the power rule. You're going to use that rule where you move the power out to the front and you reduce the power by 1. Okay, and then make sure you know how to do instead 2 to the x, which is what we first learned how to do today. Okay, so this, you're going to use the rule for exponential functions. In other words, there's a difference between x squared and 2 to the x. Okay, x squared is just a polynomial. 2 to the x is an exponential function. Make sure you know that. All right, so for our final 2 examples, let's do a couple word problems where we maybe apply some of this stuff. So let's say the number of cable subscribers from 1980, and we're going to call this time equals 0. So we're going to start counting at 1980 to the year 2020 is given by the following. S for subscribers of T. Okay, and let's say this is the pattern. It's 11 times the natural log of T and then plus 29, where T is the years after 1980. And S of T is the number of subscribers in millions. So I'm going to ask you two questions, and you have to know which one wants you to use the derivative and which one do you not need to use the derivative for. So I'm going to put these questions side by side. We're going to write out both questions first. How many subscribers will there be in 2020? But question B is, what is the rate of change of subscribers in 2020? Alright, so this question asks how many subscribers there are, just what's the number of them. This one asks for the rate of change. Okay, so the question you need to ask yourself is, which one is really asking you for the derivative? Okay, well, rate of change is synonymous with derivative, right? So this one is really asking you for the derivative. This one isn't. This one's just asking you for subscribers. So actually, you just need to identify what T is in 2020. Okay, notice 1980 is times 0, right? So 30 years later would be, 40 years later would be 2020. So T is 40. So if you're just being asked to find how many subscribers, you're just going to plug in T equals 40 to S of T. In other words, it's actually not a business calculus question. It's really just an algebra question. So if I want S of 40, I'm just going to do 11 times the natural log of 40 plus 29. Okay, so let's take out my calculator and figure that out. So 11 times ln of 40 plus 29. We're not going to get a pleasant answer, but we can round it maybe to 2 decimal places. That's kind of my go-to decimal places. So it's going to be 69.58. Okay. If you tell me on a test that that's the answer, you're going to get some credit, but you're not going to get all the credit. It's not 69.58 people. Remember, if you read the problem, the subscribers are in millions. So I would want you to say that it is around 69.58 million subscribers. And the reason I said around is because we rounded that answer anyway. By the way, that little squiggly equal sign indicates that I have a rounded answer. It means approximately. Okay. Part B, however, asks you for the rate of change. Okay. So anytime you see the term rate of change or slope of the tangent or anything like that, rate of change means find the derivative. In other words, we need to find the derivative of S. So make sure you use the right letters. It'll be S prime of T, since we're using T rather than X. So go back up here, right? If I take the derivative, the 11 is going to pull down, right? Because that's a constant we're multiplying. The derivative of ln of T is just 1 over T. just like it would be 1 over x if we were using x. And then remember the derivative of a constant's just 0. So written a little nicer, it's just simply 11 over t. So I'm going to circle this, but this really isn't my final answer because I'm also being asked to tell exactly what the rate of change was in 2020, right? So this time, rather than plugging in t equals 40 to the original equation, I'm going to plug it into s prime of t because I want the rate of change. So s prime of 40 is just going to be whatever I get when I do 11 divided by 40. Okay, so this comes out nice. Notice I don't use a squiggly equal sign. I just say it equals 0.275. Make sure you understand how to say this, though. This means that the subscribers are increasing. By the way, it's an increasing because it's a positive derivative, but it's increasing by 0.275 million per year in 2020. In other words, we're not saying there's 0.275 million in that year. We're saying the increase is 0.275 million. Because actually this is the number of subscribers. So think of a rate of change like you should have something per something, usually a unit of time. So a number per unit of time. All right, so last problem on this lecture. In Business Math 1, we talk a lot about investments. And we're going to talk a little bit about that this semester. Not near as much as we did in Business Math 1, though. But let's say an investment earns 4% interest compounded continuously. Now, just a little side note, there are not very many investments that do compound continuously. But the formula, if we're not compounding continuously, is actually a lot more complicated. So in Business Math 1 or Algebra, whichever class you took, the formula for the accumulated amount is, a lot of teachers refer to this as the PERT formula. So it's P times E to the RT power. Okay. When I say recall, I just mean recall from Business Math 1 or an algebra class. All right. So let's say part A, I want you to find the instantaneous rate of change in the account after 2 years. In other words, how much is the account going up after 2 years? If we save this money and we're earning interest, what kind of boost in interest are we getting? Or not interest, but what kind of boost in money are we getting? So I asked for the instantaneous rate of change. Okay, so first we probably need to know what the formula looks like. So first let's come up with our formula, right? So we're going to have A of t equals, P is your starting value, so that's your principal. So it's 1,000, and then E to the 0.04 t power. R stands for rate, so we're getting 4%. That's where I got the 0.04 at. So a little confusing. I'm doing this one because it's like one of the ones from your homework. This right here is a little strange looking. This is just like B to the t, but B is going to equal E to the 0.04 power. Okay. In other words, this is like E to the 0.04 power and then to the t power, because all we do is multiply those exponents anyway. And it's important that you know this so that we can do the derivative. Okay, we only have a derivative formula for B to some power. All right, so first of all, how do we know we need to find derivative? It's because of what I underlined, right? The instantaneous rate of change. So what's going to happen with the 1,000? It's a constant, so we just pull it down. Okay. And then the derivative of e is just itself. But then it's going to be times the natural log of the base. But remember, we said b was 0.04. So I'm literally just using the formula for any base derivative. So if you clean that up just a bit, for instance, the natural log of e is going to cancel each other out. Okay, so I'm going to clean this up. This is just like 1,000 times e to the 0.04t power, and then times 0.04, because algebraically natural log and e cancel each other out, leaving only the exponent. But then you could verify that on your calculator too, by the way, but then you could do 1,000 times 0.04. So 1,000 times 0.04 is 40. So you end up getting that the derivative formula is 40 and then e to that 0.04t power. So I'm going to circle this because we're going to use it. So if I want to know what the rate of change is 2 years in, I just need to plug in 2 to my rate of change formula. Rate of change meaning derivative. So if I do 40 times e to the 0.04 times 2 power, and I round it to the nearest dollar because it is money, then I'll get 43.43. And make sure you write it as a rate of change. This is per year. So in other words, I'm getting an increase or a boost to my account of 43.33 a year at the 2-year level. All right, so last part. Find the instantaneous rate of change of the amount in the account at the time that the amount is equal to $2,000. So rather than giving you a specific time period like I did in Part A, I'm asking you to kind of find what time it would be that you have an account balance equal to $2,000. All right, so if you can pull in this step right here, okay, so if we can just take from the previous problem so we don't have to reinvent the wheel, we got that the derivative formula was, I'm taking it from this step right here, okay, that I starred up there. The derivative formula was 1,000 e to the 0.04t power and then times 0.04. Like after we simplified the natural log of e part. But notice that this is just what we started with. So in other words, if we can kind of algebraically simplify this, this is really just 0.04 times the original formula. Okay, but the original formula is telling you how much is in the account right now. So now we can just plug $2,000 into that because that's the amount we're supposed to say is in the account right now. And then if you multiply that, you'll get $80. So notice this would still be per year because, and I spelled instantaneous wrong. Should be like another A in there. But if we want the instantaneous rate of change, that's why I referred back to the derivative. So there'll definitely be one in your homework just like this. I think the last question is a little tough just because it's a little algebraically specific. Okay, but finance formulas kind of generally are like that. Okay, so maybe try to pause the video if helpful, and then maybe try to look at your homework as well at the same time.